Hello to everyone, I'm Rosalia Tufana and I'm going to talk about the paper Towards Automating Code Review Activities. In this work we have made a first step in the direction of partially automating the code review process. But before to go into details, let's start defining what is a code review and why we decided to focus on this activity. Code review is the task of analyzing the code written by a teammate to recommend how to improve its quality, for example by catching bugs or suboptimal implementation choices. Recent studies provided evidence of the benefits of code reviews, but the problem is that this is a very time-consuming activity that keeps developers busy away from their main task. So we believe we can reduce the cost of this process by automating part of its activities. And the final goal is not to replace developers during code reviews, but instead work with them by automatically solving code quality issues. So now let's see how a code review works. First of all, there is a contributor who is the developer reading the code and submitting it for the review. Then the code is reviewed by one or more reviewers who can recommend code changes in natural language. And then the contributor revises the code implementing those changes and creating a new version of the submitted code. And this process can be iterated several times until the reviewer is happy with the implemented changes. So usually there are several rounds of review, and during each of these rounds and during each of these three steps, a piece of data is created. In particular, we have in step 1 the submitted code, in step 2 the natural language comment, and in step 3 the revised code. So what we want to do is to mine these pieces of data in order to automate specific code review tasks. So the first thing that we did was to collect a dataset of these triplets from Gerrit and from GitHub platforms, and it counts in total nearly 900,000 triplets. Now, using the entire dataset as it is simply unthinkable, both because the dataset contains a lot of noise and because of the limitation of the model we are going to use. So we cleaned this initial dataset, having in mind that first of all we decided to work on method level, which means that we look at changes recommended by reviewers on specific comments in isolation without looking at the entire file. Moreover, we focus on those methods that receive just one useful comment. And finally, work on raw source code requires more complexity for the model, so we decided to adopt an abstraction process and work on the abstraction code. So to be more clear, here we have an example of an initial data from Gerrit, and I want to show you what we obtain as a final triplet. So first of all, we have an entire file under review. On the left side, we have the entire submitted code, and on the right side, the entire revised code. Then in the part highlighted, you can see that we have two comments, but the second one is clearly just a reply to the first comment, and it is useless for our goal because it does not provide any useful information on how to improve the code. So we can simply ignore it, and in this way we have just one useful comment. Then we know exactly which part of the code the comment refers to, and using this information we are able to isolate and extract the method the comment refers to in the submitted code. Now, using the signature of this method, we are also able to isolate and extract the same method but in the revised code. So the same method but modified. And so what we have at this point is the submitted code corresponding to a single method, one comment in natural language, and the revised code corresponding to the revised method. Now the next step is the abstraction of the code. To abstract the code, what we do is to replace the literals and the identifiers with specific numbered identifiers, which simply give information about the type of the literals or the identifier they are replacing. And of course, we do the same thing both with submitted code and the revised code using the same abstraction map. And so finally, we have the final triplet. Now, to get only triplets made in this way, we had to apply many filters to the initial dataset. I don't have time to explain all of them, but you can find all the description in the paper. Now, to give you one concrete example, we built an heuristic to automatically exclude meaningless comments, such as the useless one that I showed you before in the example. So at the end of this filtering process, we got a dataset consisting of 70,000 triplets, and using this dataset, we want to train two different models in order to automate two specific tasks in the context of code review. So going back to the code review overview, we want to automate one task on the contributor side and one on the reviewer side. On the contributor side, what we want to do is provide the developer with a preliminary version of the revised code, but skipping the reviewer interaction. So we want to generate the code implementing changes likely recommended by reviewers. In this way, the contributor can submit for review a first better version of the code. On the reviewer side, the goal is to obtain a preliminary version of the revised code, but this time implementing the suggestions of the reviewer contained in the comment. In this way, the reviewer can provide as review not only a comment in natural language, but also an example of how they would like the suggested changes to be implemented. So, in order to do that, we trained two different models using two different versions of the same dataset. On the contributor side, the training set consists of only the submitted code and the revised code. Using this training set, we trained a transformer model that is an encoder-decoder model. The encoder takes as input the submitted code, and the decoder tries to generate the revised code. On the reviewer side, instead, we want to take as input both the submitted code and the natural language comment, and generate the revised code implementing the suggestions contained in the natural language comment. And for this case, we modified the architecture of the classic transformer in order to have two encoders and one decoder. The two encoders take as input one the submitted code and the other one the natural language comment, and again the decoder tries to generate the revised code. Then for both models we decided to apply a beam search strategy. In few words, it means that the models can generate not only the most likely prediction, but the k most likely predictions. And we explored different values from the beam sides, in particular 1, 3, 5, and 10. Okay, finally we evaluated our models on perfect predictions. With perfect prediction we mean a model prediction that applies exactly the same changes made by the developer to the submitted code during a real code review activity. The models were able to generate a perfect prediction on 3 up to 16% of cases on the contributor side, depending on the number of predictions the model is allowed to generate, and on 12 up to 31% of cases on the reviewer side. Besides computing the perfect prediction, we also performed additional analysis related to the BLEU score and the Levenshtein distance, and also a qualitative analysis on the predictions. You can find details in the paper, and I also want to point you to the replication package where you can find the code, the data, and the results of the analysis we performed. So to conclude, I want to briefly summarize the whole work. We investigated the possibility to automate specific code review activities using transformer-based models trained on a dataset of 17,000 triplets built mining real code review activities data. We assessed their performance in terms of perfect predictions, finding that when allowed to generate 10 different predictions, they are able to provide a good prediction on 16 and 31% of cases. Thus, while achieving some promising results, it is clear that there is still a long way to go to automate code review related tasks, and we are now investigating how to improve performance using pre-trained deep learning models and a larger dataset that we're building. Thank you very much for your attention, and feel free to reach me using one of my contacts.
Hi everyone, so I'm sorry for the interruption to today's stream. The schedule was not correctly entered, and so the previous pre-recorded video of the presentation that was due to play out has not played. With me we have the session chair and the author for the previous paper that was supposed to be doing a Q&A now. I'm going to invite them to briefly introduce themselves, and then we'll play out the pre-recorded presentation, and then I encourage you to join them in the discussion room that will become available so you can participate in the Q&A separately outside the stream. Thank you. So I'd like to hand over if you just briefly introduce yourselves.
Yeah, so hello everyone. I am Rosalia Tufano and I'm a PhD student at University della Svizzera Italiana. And yeah, my work is about is a first step on automating code review activities. And I hope you can enjoy the video now. I'm sorry for the
inconvenience.
Inconvenience.
So sorry once again, and I'll click play on that video now for you. Please do join the Q&A discussion room after the video ends. Thank you.
Okay.
Hello to everyone, I'm Rosalia Tufana and I'm going to talk about the paper Towards Automating Code Review Activities. In this work we have made a first step in the direction of partially automating the code review process. But before to go into details, let's start defining what is a code review and why we decided to focus on this activity. Code review is the task of analyzing the code written by a teammate to recommend how to improve its quality, for example by catching bugs or suboptimal implementation choices. Recent studies provided evidence of the benefits of code reviews, but the problem is that this is a very time-consuming activity that keeps developers busy away from their main task. So we believe we can reduce the cost of this process by automating part of its activities. And the final goal is not to replace developers during code reviews, but instead work with them by automatically solving code quality issues. So now let's see how a code review works. First of all, there is a contributor who is the developer reading the code and submitting it for the review. Then the code is reviewed by one or more reviewers who can recommend code changes in natural language. And then the contributor revises the code implementing those changes and creating a new version of the submitted code. And this process can be iterated several times until the reviewer is happy with the implemented changes. So usually there are several rounds of review, and during each of these rounds and during each of these 3 steps, a piece of data is created. In particular, we have in step 1 the submitted code, in step 2 the natural language comment, and in step 3 the revised code. So what we want to do is to mine these pieces of data in order to automate specific code review tasks. So the first thing that we did was to collect a dataset of these triplets from Gerrit and from GitHub platforms, and it counts in total nearly 900,000 triplets. Now, using the entire dataset as it is simply unthinkable, both because the dataset contains a lot of noise and because of the limitation of the model we are going to use. So we cleaned this initial dataset, having in mind that first of all we decided to work on method level, which means that we look at changes recommended by reviewers on specific comments in isolation without looking at the entire file. Moreover, we focus on those methods that receive just one useful comment. And finally, work on raw source code requires more complexity for the model, so we decided to adopt an abstraction process and work on the abstraction code. So to be more clear, here we have an example of an initial data from Gerrit, and I want to show you what we obtain as a final triplet. So first of all, we have an entire file under review. On the left side, we have the entire submitted code, and on the right side, the entire revised code. Then in the part highlighted, you can see that we have 2 comments, but the second one is clearly just a reply to the first comment, and it is useless for our goal because it does not provide any useful information on how to improve the code. So we can simply ignore it, And in this way, we have just one useful comment. Then we know exactly which part of the code the comment refers to, and using this information we are able to isolate and extract the method the comment refers to in the submitted code. Now, using the signature of this method, we are also able to isolate and extract the same method but in the revised code. So the same method but modified. And so what we have at this point is the submitted code corresponding to a single method, one comment in natural language, and the revised code corresponding to the revised method. Now the next step is the abstraction of the code. To abstract the code, what we do is to replace the literals and the identifiers with specific numbered identifiers, which simply give information about the type of the literals or the identifier they are replacing. And of course, we do the same thing both with submitted code and the revised code using the same abstraction map. And so finally, we have the final triplet. Now, to get only triplets made in this way, we had to apply many filters to the initial dataset. I don't have time to explain all of them, but you can find all the description in the paper. Now, to give you one concrete example, we built an heuristic to automatically exclude meaningless comments, such as the useless one that I showed you before in the example. So at the end of this filtering process, we got a dataset consisting of 70,000 triplets, and using this dataset, we want to train two different models in order to automate two specific tasks in the context of code review. So going back to the code review overview, we want to automate one task on the contributor side and one on the reviewer side. On the contributor side, what we want to do is provide the developer with a preliminary version of the revised code, but skipping the reviewer interaction. So we want to generate the code implementing changes likely recommended by reviewers. In this way, the contributor can submit for review a first better version of the code. On the reviewer side, the goal is to obtain a preliminary version of the revised code, but this time implementing the suggestions of the reviewer contained in the comment. In this way, the reviewer can provide as review not only a comment in natural language, but also an example of how they would like the suggested changes to be implemented. So, in order to do that, we trained two different models using two different versions of the same dataset. On the contributor side, the training set consists of only the submitted code and the revised code. Using this training set, we trained a transformer model that is an encoder-decoder model. The encoder takes as input the submitted code, and the decoder tries to generate the revised code. On the reviewer side, instead, we want to take as input both the submitted code and the natural language comment, and generate the revised code implementing the suggestions contained in the natural language comment. And for this case, we modified the architecture of the classic transformer in order to have two encoders and one decoder. The two encoders take as input one the submitted code and the other one the natural language comment, and again the decoder tries to generate the revised code. Then for both models we decided to apply a beam search strategy. In few words, it means that the models can generate not only the most likely prediction, but the k most likely predictions. And we explored different values from the beam sides, in particular 1, 3, 5, and 10. Okay, finally we evaluated our models on perfect predictions. With perfect prediction we mean a model prediction that applies exactly the same changes made by the developer to the submitted code during a real code review activity. The models were able to generate a perfect prediction on 3 up to 16% of cases on the contributor side, depending on the number of predictions the model is allowed to generate, and on 12 up to 31% of cases on the reviewer side. Besides computing the perfect prediction, we also performed additional analysis related to the BLEU score and the Levenstein distance, and also a qualitative